Our next example is cosine of x. We're going to derive the Maclaurin series for that function. And so I wrote up the Taylor series formula there on the top, so we don't have to really think about that again. It's up there. But here we're going to do the Maclaurin series, so around a equals 0. So all I need to do is, as we said, we need to take successive derivatives. So I'm just going to take a couple derivatives. First derivative, cosine is negative sine. Second derivative, okay, would then be this. Next, the derivative of cosine is negative sine. And then the fourth derivative is cosine. Okay, and then we started with cosine x. Our fourth derivative is cosine x. So it's just going to keep cycling along, right? So we know they're just going to be the same. So my fifth derivative, and I can write them here, but I don't really have to. But just to give you the idea, I'm going to throw a couple at the bottom here, so that we see the pattern when we start to put in our a equals 1. 0. A equals 0. Right. Whatever. So now I'm going to evaluate these at 0. And you'll see what we have, right? So starting off, what I'm going to put it here, f of 0 is cosine of 0 is 1. Okay? First derivative is 0. Second derivative, negative 1. Third derivative is 0. Fourth derivative is 1. And I was at the fourth derivative. Now, so I got 1, 0, negative 1, 0, and it's going to repeat. So it's going to be 0, negative 1, 0. Five, 6, 7, and then if I do 8, plugging down at the bottom here, we can hardly see it's going to be 1 here. Okay, so fine. Now, remember though, we don't just need this, we need it in that form. We have to divide by n factorial, right? So Cn is this derivative divided by that n factorial, so it's going to give me C0 is 1. C1 is 0, C2 is minus 1 over 2 factorial, C3 is 0, C4. So you'll notice, of course, that because it's sine and cosine, half of these guys are 0, right? So that's kind of nice. It's like half of my terms are 0. So I sort of have to do a few more terms, perhaps, to see what I'm at. So 6. Whoops, 6. Okay, so there's my C. So now if I write this out, this is the sum from n equals 0 to infinity of these Cn's, x to the n. So I have 1 plus 0 plus 1 over 2 factorial x. Oh, I forgot minus, right? Minus is there. All right? And then my next term is, so you'll notice, first of all, as I'm writing these out, that the odd terms are 0. I'm just going to, which, if you think about it, it makes sense because we know that cosine is an even function. So, it's an even function, and its expansion as a Taylor series is going to be all even powers of x. So that's kind of cool, right? So now if I want to write this out, there's various ways of writing this, but the easiest thing is to notice that, all right, I've got n is 2n, right? Everything's 2n, right? So if I do n equals 0 to infinity, and I just put it in 2n as x to the 2n over 2n factorial, and I've got minus 1. I want to start with, so it should be maybe n plus 1 or n minus 1. I don't care. That's kind of stuck in there. Let me make that look a little bit prettier. No. Maybe it's 1 to the n, right? Because if I'm starting from n equals 0, I need something that is even, and n equals 1 should be odd. So it should be minus 1 at the end. All right, so there we have our nth term formula. And again, to check for the radius of convergence, you would do the ratio test, but I'm just going to cheat and tell you that the radius of convergence here is equal to infinity. I don't think we did this one. I think I'm going to do sine next. I think we did do sine somewhere, but anyway, so here it is. By the way, there's a sheet on Canvas which has all of these kind of written on it. So if you just want to use it as print it out or just keep it somewhere and use it as a reference, it's convenient. Once we've actually done it in class, you don't have to redo that particular series. You can just use it. If it's on that sheet, you can use it. Okay, series cosine of x. So let's do sine and sort of just think about it for a minute. We might imagine that we can have a similar thing, that it'll happen in a similar way. And it will. But as I said, cosine is an even function and sine is an odd function. So if that pattern continues, sine should be all odd powers, the way cosine was all even powers. So let's see. We're going to do exactly the same thing. Take these successive derivatives. Derivative of sine is cosine. It's going to be quite similar, so I'm going to pull it through pretty fast here. Derivative, here's our 4. I'm going to get my sine x back. And then the next ones are just going to keep with the same program. So honestly, the reason I'm going down to 8 in this case is so that we can see so we can see it continue, and also because I know a bunch of these are going to be 0. Okay. So if I'm looking for a pattern, so keep going until you see the pattern is one thing. And then the other thing is make sure that you have enough non-zero terms. So sine of 0 is 0. So here with C0, the constant term is going to be 0, right? Oh. Look. Wait, what's going on here? Oh yeah, that's right. Okay. This one goes with this one. This one goes with this one. All right, that's why I was, what am I doing? There we go. Now we're confusing my own self. And it does look like we got zeros on the even terms and numbers on the odd terms, so that's good. Okay. Now, remember, this is the Maclaurin series. That's why we're putting in 0 here for our A. If we were asked to do a Taylor series around some other point, we would still do the process of taking these successive derivatives, but then we would be putting the value of that point in there. And I'll do an example like that in another video. Because those tend to get, I think, a little more confusing, but let's just stick with these first. Okay, so C0 is 0, because remember we have to do to get the CNs, we have to divide by our n factorial. So if I just keep going through, C6 is 0, C7, my 7s are looking like Z's today. Okay, so that gives us about 5 terms, and that's always nice. I think that you should write down at least 5 terms of your series, 5 non-zero terms of your series. More, that's 4. Okay, 4 or 5. I like 5. We'll just throw the 5th one on because we see the pattern now. Okay, so that's going to tell me that sine x, cn x to the n, but c0 is 0, so my first one is going to be x. Then I've got minus x cubed over 3 because c2 was 0. So just by the way, the last time I wrote in the zeros, just so that it was clear to you guys what I was substituting in for. Plus minus, yes. But in this case, I'm just not going to write down the zeros because we've already seen it in note, right? So you have something like this. All odd terms. So we're going to write down, okay, my nth term. Okay, first of all, I'm going to do, because I'm starting from n equals 0, I'm going to do x to the 2n minus 1 over 2n minus 1 factorial. And then again, I've got minus 1, but I want the even ones. If it is 0 and 2, 0, 1, 2, to the end. Okay, so there's my nth term formula. And again, the radius of convergence here will be infinity, and I'm pretty sure we actually did this example or something very like it with the 2n minus 1 factorial in the bottom. That was pretty familiar. So we can do this with the ratio test, and we will show that the radius of convergence there is in fact infinity. All right, one other thing I wanted to talk about before going on to the other examples is we can use this particular example because if you look at my little graphs, I graphed sine of x. But sometimes they talk about Taylor polynomials, okay? So the question is, what are Taylor polynomials? This is the Taylor series, or the Maclaurin series in this case, but in general, the Taylor series. The Taylor polynomials are just the partial sums. So if I take my series here, and I look at the Taylor polynomials for it, let's see, T1 would be taking, T0 would just be the nth zeroth term, so that's just x. T1 would be x minus x cubed over 3, this sort of thing, okay? So these are, remember, actually polynomials, right? Here's the linear, and here's T2 of x would take us up to n equals 2. So these are just called the Taylor polynomials. And these are what we actually use in practice when we're using the Taylor series to approximate something and or to simplify a problem. We're going to use one of these finite approximations to our function. Okay? So in physics, you might want to use, maybe linear is too easy, too simple, unless you're really close. You might want to use this one, a nice cubic approximation. This is a very good approximation for that function. And depending on what you need, you can go out to wherever you want. But those are the Taylor polynomials. And again, in terms of if we wanted to show that the Taylor series really was converging to this function, what we would do is we would write down, okay, the finite one, say you would write down your f of x as being your Taylor approximation as n plus some remainder term. The remainder term, of course, gives you a measure of the error of the original from the original function and the polynomial. And then you show that this one goes to 0 as n goes to infinity. So I'm not, as I said, not going to do that proof here, but that's basically the way it goes.